Today's topic is torsion of circular shafts. In this class, we're going to be dealing exclusively with circular cross-sections when it comes to torsion. When you have a non-circular cross-section, there are other effects such as warping that come into play, and we're not going to deal with that in this class. So the first thing I want to do is just go over a basic overview of the deformations that we observe when we have torsion. So if we have a cylindrical member and our coordinate system, we can use X, Y, Z, but oftentimes it's going to be more convenient for us to use cylindrical coordinate systems. So we're going to put our Z axis along the length of the member. R will go from the center outward. Theta is then perpendicular to R and Z. So theta is always going to be tangent to your cross-section. And sorry, not cross-section, tangent to the circumference of your cross-section. And so you can imagine Z is always going to be constant, but R and theta can rotate around that cross-section so that they can point in any direction, right? R can be in any radial direction, theta will always be perpendicular to it. So when we have this, we apply stresses on the ends of the member such that we have a moment about that Z-axis. So we're going to apply some type of stress just on this cross-section such that we end up getting some type of moment about the Z-axis. And we call that capital T for torque. That's our torque that's being applied. But the sum of the forces have to be equal to 0. So even though we're developing a moment, there's no net force to this object. The other key thing is that in this, this application of pure torsion, we have no stresses on the lateral boundary. So we just have stresses on the ends, and those are causing a moment about the Z-axis. When we do this, we see 5 distinct behaviors. One is that as we twist this object, so those of you with siblings, you remember, depending on whether you're the younger or the older sibling, you either got your arm twisted or you twisted your friend's, your sibling's arm. Okay. So you take your hands, you move them in opposite directions. That's essentially you putting torque onto the arm. And when we do that, what we'll notice is that the diameter is unchanged. And so if the diameter is unchanged, that diameter runs in the radial direction, correct? So if the diameter is unchanged, what do you think we can say about the strain? Right. So the strain in the R direction is 0. No change in dimension. And wedges are unchanged. And what I mean by that is that if we're looking at our cross-section, and that cross-section has these little wedges drawn on it, what I'm saying is that they still look like that they don't get smaller or wider. So what direction is that? Is our theta?
I don't know what that is called, like weird shape.
Theta.
Theta. I was meaning something else, but what was it called?
We'll go with theta.
Okay. Oh,
You mean theta.
I was you already used that.
Yes, this
Oh,
one.
the top. The one
Yes,
on top.
yes, that's the
And
direction.
black, I don't know what's that called.
Theta.
No, the black. That's R. Is that R? Yeah.
This one here? Yeah, that's R.
No.
Okay. All right, so everyone on board that if these pi shapes are not squeezing or contracting, we have no change in our theta direction. All right, that means our strain in our theta direction is 0. The other thing we see is that our length is unchanged. So what do you think that means?
Strain is 0.
Good. Furthermore, when we do this, we see that the cross sections remain perpendicular to the z-axis. So if I have some, so let's take our member here. If we're looking along the length of a member, that's our z-axis, and this has a series of cross sections, we don't see those cross sections tilting at all. They stay perpendicular to the z-axis. So what do you think that says?
Don't we kind of already see that from the strain in the R and theta direction things here? Because that would be like a perpendicular plane. So if there's no.
Conceivably, you could have this tilting with your diameter still staying the same.
Shears. Oh, shears.
Yeah, this is going to be a shear strain.
That's the weird thing I was talking about.
Gamma.
Gamma.
Gamma. All right. Which shear strain, though? What are the two coordinate directions that are involved in this? We start out with 2 lines. In which directions? Okay, I'm gonna give you R. That's good, but it's not theta. What's the other? What is perpendicular? Z. Right. RZ. So you have a line in the radial direction and a line in the Z direction, which are originally perpendicular, and I'm saying that stays perpendicular. That radial line doesn't tilt. All right, we're running out of things to calculate. No curvature of radial lines. So that means if you have your cross section, once again, you have your cross section, and it starts out like this with the lines in the radial direction. What I'm saying is that those lines do not go like this. They don't curve. So what does that tell you? Good. Right, so initially these directions, oh wait, no, did you say theta z? Halfway good, halfway good. Yeah, you have 3 choices. Okay, so these lines that are initially perpendicular are in the R direction, right? That's your radial direction, and then your theta direction. And so I'm saying that that angle does not change. So everything is 0, except for what? Gamma theta z. Perfect. So gamma theta z is the only non-zero quantity when we apply this torque. And so this is what that gamma theta z looks like. If we have a line, that blue line, that initially is along the length of this member, and then we apply some torque to this, you're going to see that that line is going to be kind of traveling away at an angle. So we're going to get strain. We're going to change in the theta z direction. So if we look at our theta direction, that is theta direction. Let me color. Theta direction is that direction. Z direction is this direction. Initially, those are perpendicular. And when we get to the pink line, they're no longer perpendicular, right? We've changed that angle. Back here at the far end, I'm calling this point Z. The length is delta Z, so on the right-hand side, you're at Z plus delta Z. At both sides, we could have some relative or some rotation, and that angle of rotation between the angle of rotation measured in the cross-sectional plane between the initial position and the final position is given by the angle phi. So phi, this is the phi that occurs at Z plus delta Z. This is the phi that occurs at Z. You don't necessarily have 0 on the left end. If it were fixed on the left end, you would have 0. But assuming that we're just taking some little cut out of a bigger member, you're going to have some phi angle on both sides. Now the arc length is calculated as your radius times your angle, correct? So that's why we have R times phi, and then everything in the parentheses is a subscript, just telling you where phi is being evaluated. So phi is what we call the angle of twist, and it refers to a particular cross-section. So if you have an angle of twist value, it's at a particular cross-sectional location, so somewhere along the length of that member. So if we draw this out again, looking at it, let's say that's our initial blue line. Now we're looking at it from the side. And so that's our initial blue line. And that pink line, I don't actually have a pink on here, so maybe we'll make it purple. That line's going to look like that. That's what we're going to see if we're looking at this from the side. And here on the left, we had R phi of Z. And on the right, we had R phi of Z plus delta Z. Now, if we're assuming small angle, which we always do in this class, what is tangent of alpha? Not that it matters, but let me give you alpha before you answer that question. Let's call this angle alpha. So what is the tangent of alpha equal in small angle assumption?
Yeah. Alpha.
Alpha. Tangent is sine over cosine, and sine of a small angle is that angle. Cosine of an angle is 1, so we get alpha. So what that means is if I initially had a z-axis and a theta axis, and then I apply this torque, and now a line that was initially in the z direction is in this inclined direction, and I'm saying that that's an angle alpha. What is that alpha equal to in terms of what we've been talking about in this class? Yeah, that's my shear strain, right? So this is equal to gamma theta z. That's my angle of closure. So now the trick is, can we quantify or get an equation to calculate what this gamma is? Can we calculate alpha? Perhaps more easily, we can calculate tangent of alpha, because we have here what appears to be a triangle. So tangent of alpha is opposite over adjacent. The opposite is going to be R phi of z plus delta z minus R phi of z, right? You need to subtract out, if this continues down, you need to subtract that amount out to get this leg here, that opposite leg. And then we're going to divide that by the adjacent leg, which is delta Z. So this is the equation for gamma. But if we want to know gamma at a particular point, we're going to take the limit as delta Z goes to 0. And so that tells us that gamma phi Z is equal to R. I can pull R out of that equation. It occurs in both terms in the numerator. And then what's left is the change in phi, so delta phi over delta Z. And if I take the limit as delta Z goes to 0, what I get is d phi dz.
I got lost where you started doing that triangle.
Mm-hmm.
Is that the length of the arc on the left side of that triangle?
Yes, let me highlight this. This length here in this non-visible yellow is this length here. That's your arc length.
Okay.
And then on this right-hand side, this green is that arc length. So we're looking at the shaft from the side. And then we're noticing that it looks kind of like a triangle. And then we're using that to help us calculate that angle, which we know is approximately the tangent of the angle and also equals our gamma value, because gamma is defined as the angle of closure. And so this turns out to be equal to R d phi dz. And now we can give this a very special name, this d phi dz. So the change in phi as you go along the length of your member is what we call the rate of twist. So that is how quickly your angle of twist is changing. So the angle of twist is the actual angle measured at some location. The rate of twist is how quickly that's changing with respect to the length of your member. Now R can take on a value between 0 and C. C is what we call your outside radius. So if we want to maximize this equation, so if we want to maximize the shear stress, we're going to choose the biggest possible value of R, correct? So that means that we're going to choose C d phi dz. So another way we can write that is we can say C over R times gamma phi z. So if you know the shear strain at any location R, so at any value of R, if you know the shear strain, you can then calculate the maximum shear strain that happens on the outside of that member.
What was it when you divided by z or delta z?
Yes?
Yeah,
What?
what was that from?
Delta Z is the horizontal dimension of that triangle.
Yeah, and the tangent of alpha. How did you get that?
Small angle tells me mathematically the tangent of alpha is approximately equal to alpha. So the tangent of an angle is approximately equal to the value of that angle. And I can see that that angle is equal to my shear strain, so I want to evaluate it. All right, we're gonna look at our material relations. So if we look at Hooke's law, remember generalized Hooke's law? It said that our three strains, in this case, let's put them in order. Strain R, strain theta, strain Z. These always have to be in the same respective order. So like X, Y, Z maps to R, theta, Z. So these are all functions of sigma r, sigma theta, and sigma z. I think I may have said that. I think I said that backwards. Well, these are functions of strain. All right, so if you know your 3 strain components, you can then calculate your 3 stress components. What are our 3 strain components? Normal strains?
Is it X, Y, Z?
No, like what's the numerical value in torsion? 0. So this one is 0, that one is 0, that one is 0. Therefore, sigma r equals 0, sigma theta equals 0, sigma z equals 0. Torsion does not cause any normal stress in this member because all 3 of our normal strain components are 0. So let's look at shear. Shear has 3 equations, and in each of those equations, our shear stress is equal to G times gamma. 2 of these are going to be equal to 0, right? Because 2 of our shear strains are equal to 0. Oh, that's no good. In particular, tau RZ and tau theta R equals 0. But we have a gamma in the theta Z direction that is not equal to 0. So I can say that tau theta Z is equal to G times gamma theta Z. And we just calculated what gamma theta Z is equal to. All right, we said that it's equal to some radial value times d phi dz. And if we want the maximum value of theta z, we're going to say gc d phi dz. Or G times C over R times tau theta Z. So if you know the shear stress at some location on the cross section, you can get the maximum by amplifying it. Oh, you know what? I don't think we need that G there. You can get the maximum by amplifying it by C over R. So what this is saying is that if we look at this member, and this member has the Z direction and the R direction, what it's saying is that our shear stress is linear. As R increases, our shear stress increases linearly. So those shear components are always directed in the theta direction. So they're going to be kind of making a circle around the cross section. If we have a material element out here with sides that are in the theta and Z direction, this is going to result in some type of shear. And there will be no normal stresses, just shear, right? But I want you to keep in mind always that although that may be what we're typically interested in, if you look at some other orientation, you will end up with normal stresses, and at some orientation, say 45 degrees away, you're going to have your principal stresses. So it's important, just because we're talking about torsion doesn't mean that there's not normal stress in this member. It just means that when we're looking at a material that's in the R theta Z orientation, there's no normal stress on that orientation. Okay. All right, so let's go ahead and try to draw the Mohr's circle for this. What does your Mohr's circle look like when you have tau as your shear stress and you have no normal stresses? No, not a line. Where's your center going to be? At the origin, because your average of 0 and 0 is 0. And then you're going to plot sigma x and tau.
So it's going to be one on the tau axis.
Yeah. Which I think I know why you said that it was a line. But just remember, you always need to make it into a circle. Okay. You have your sigma x is 0. Plot that with tau xy, so you get that point below. Then, assuming that we have positive shear stress, and then your sigma y is 0, plotted with negative tau xy, so that gives us the point above, and then we make our circle. So this brings up kind of what is positive, what is negative. Remember that if your shear stress is pointing in the positive direction on a positive face, that's positive. So your Z positive is in this direction. The way that I've drawn that there, that's, well, it's easy to get yourself confused. Don't fall into the trap I almost fell into. R is coming up out of this. Right, R would be coming out of that element. So which way is theta going? Is theta going up to the top or down to the bottom? We're looking at this here. And the R-axis is coming out. It's always coming out of your member. Z I have drawn to the right. So my question is, what direction is theta? Is it going up and over towards the top or down? Going down and around? And why do you say that? All right, you just want to go the same way as the shear stress? All right.
It's like right hand rule.
Because R times theta has to equal, it's like the right hand rule.
Yeah, R times theta has to equal Z, right? X, Y, Z, R theta Z. So if you had your X coming towards you and your Z going towards the right, your Y would have to be going down. It's the same thing with the cylindrical coordinates. But it's easy, because things are circular, it's really easy to get yourself turned around and think that theta is going the wrong way. So that's the way it's going to be. So now on our Z face, we have a positive theta direction shear force. So that tells us that that's positive shear stress. Applying a positive torque means that on your, so you have, if you have this face, and you're coming out like this for your positive Z direction. So on that face, if you do your right hand rule where you put your fingers in the direction of the torque, your thumb will be pointing in the positive Z. That tells you that's a positive torque. And then it's the opposite on the other end. So on the end of this rod that's going to be pointing in the negative Z direction, then your positive is with your thumb pointing in the negative Z direction. So really, it's always pointing away from that member for your positive torque. And positive torque is going to give you positive shear. So when we were doing axial loading, we took our stress-strain relationship, our Hooke's law relationship, and we put in the values for stress and strain that pertain to that loading, right? The P over A and the delta L over L. So we want to do a similar thing here. We want to kind of take our shear stress strain relationship, but put it in terms of what we have going on for this particular stress and strain. It's not quite as simple here though, because we don't have a uniform stress field. And so I can't just calculate tau. It's going to depend on where we're at. So we're going to kind of do this backwards derivation and fall into the solution, if you will. All right. So we're going to start with looking at our cross section. We have this circle. And I'm going to look at a little segment of that circle that I'll say is delta theta. And if we look at just a little small element, the distance to that element is r. So the distance to the center of that element is r. The radius is c. So if we look closer at this little element, we know that the side of that element is delta r. What is this arc length? You got all the right letters, but not in the right order. Yeah. Can I say that you said this? R delta theta? Okay. So you.
Oh, because you decided that is R. Oh, never mind. Yeah.
Yes, I define, yeah. So you don't want to use delta R. It's just R times delta theta.
Because the radius is on the outside.
We're going to say delta R is small enough that the answer to your question doesn't matter, but sure. Okay. So if we want to know the area of this little segment or portion of the segment, we're going to say delta A is R delta theta. So it's small enough that it's essentially a rectangle, and we're just going to multiply those two dimensions. So the force in the theta direction that acts on that element is going to be the stress times that area. So it's going to be the stress times R delta theta. All right, so now if we want to calculate the torque, which is just a fancy word for the moment about the z-axis, we know it's going to be the force times the moment arm, right? So at any particular location, it's the force acting at that location times the moment arm. So your moment arm is R. The force is what we just computed, tau theta z, R delta theta. So we can rewrite this as tau theta z, r squared delta r delta theta. Oops. This, remember, is our moment arm. This is our force. And now I'm going to think back to the previous slide. We have already obtained an expression for shear stress, right? Relating shear to strain. So shear stress, we said previously, is G R d theta dz. So I'm going to plug that in and multiply by r squared delta r delta theta. So now I have an expression for the torque caused by the force on a tiny element on this cross section. But to get the entire torque acting over the entire cross-section, I need to integrate over that cross-section because this torque value is not going to be the same throughout, so I need to integrate. So I'm going to say that this is equal to, so this, this was the torque on an element, and this is the torque on the cross-section. So this torque is going to be equal to the integral. I'm going to integrate from 0 to 2 pi. So that's my integration with respect to theta. I'm going to integrate with respect to r from 0 to c. And I'm integrating this equation, gr d phi dz times r squared delta r delta theta. And I apologize for those of you who it's killing that I didn't make that r cubed. You will see why in just a second. Okay, so I make this dr d theta. Probably should have done that here. These deltas, if I put them in an integral, it has to be d instead of delta. All right, so I didn't want to make that r cubed because this term here should be something really familiar to you. Would you agree that r dr d theta is essentially dA? Okay. So what is that?
That one thing they do in math.
Yeah, you've done this before. Maybe in statics too. What's that? It has kind of to do with it. No.
Is it a sphere?
No. We can keep. No, it's something that you learned about in statics. Is it really chilly in here? Yeah, it kind of feels like the North Pole, doesn't it? Yeah. Yeah.
Is that a statement?
It's a hint.
Is it, that's how you go from polar coordinates to Cartesian coordinates?
We're so close. No, there's something that we do in Cartesian coordinates that we can do in polar coordinates with this equation. It's the polar. No, not even a little bit. Does the expression polar moment of area ring a bell? No. What about J? No. What about I? Do you remember capital I? All right. So there was this thing back in statics called the moment of area, also called your second moment of inertia.
Oh yeah.
Or second moment of area, moment of inertia, something like that, right? I, you had Ix, you had Iy.
Yeah.
Well, if you add Ix to Iy, you get J. Yeah. And J is your polar moment of inertia. You can calculate it by taking the integral of r squared over the area. And it's typically important for cylindrical shapes. Please go back and get very familiar with I. Right? I is important.
How did you get the delta A? That R delta theta?
Because that is the area of an incremental thing. And when we're dealing with integrals, delta, so that's delta A. When we're dealing with integrals, delta becomes infinitesimal, so it becomes D. All right, so long story short, I'm gonna plug in J, this J character that I swear we met them at a party one time, but you don't remember. So we brought J back. So the nice thing about J, I wrote over this, but it's a measure of our geometry's ability to resist torque. So it is a geometry characteristic. It has nothing to do with your material. It only relates to your geometry. But now that we've put J into this equation, it's greatly simplified. So let's see what we had. We had over here that our torque is equal to G times our rate of twist times J. So that is here. Gj times rate of twist gives us our torque. So what this means is that G is a material constant, J is a geometric constant. So if we know the material in the cross-section, and then we know either the torque applied or the rate of twist, we can compute the other one. And these questions sometimes will be asking us, so we can write the same expression in different ways and it does different things for us. So one way I'm going to write it is by dividing by J, and then it looks like this. The only reason I'm doing that is because on the next slide, we're going to use that equation. But what might be more relevant in terms of solving problems is isolating the rate of twist. So you can calculate the rate of twist with T over JG. Now that rate of twist, we can express, if we're looking over a longer length instead of an infinitesimally small element, if we're looking over some delta Z, we can now express that as a delta phi, which means the phi at location 2 minus the phi at location 1. So if we have our member here, this would be 1, this would be 2. So there's some twist, angle of twist at the second plane, some angle of twist at that first plane, and you can subtract them to get your TL over JG. So what that means, if you know the amount of rotation at 1, then you know TL over JG, you can calculate what the angle of rotation will be at a different location. So there's a variety of ways that we can ask these questions, and oftentimes it's just a matter of taking this one equation and isolating the variable that you're interested in.
What's L?
Yes, L is the length. Yes, L popped in there because d phi dz became delta phi over delta L, and then we integrated with respect to L, so that went to the other side. Or I moved it to the other side, and then I integrated with respect to L, and it becomes the length. So that's the length between cross-section 1 and cross-section 2. Other questions? All right, so 2 equations that we've already talked about. First, we got the shear stress equation. It was GR times the rate of twist. And then on the previous slide, our material relations gave us this. I want to put these 2 together. So this one I'm going to say tau over R equals G d phi dz, which now that's equal to T over J, right? Because this term here is that, and it's that. So tau over R equals T over J. So that gives us a very important equation that our shear stress is our torque applied times the radial location divided by J. So that's another extremely important equation. And if we want the maximum shear stress, it's TC over J. On the previous slide, I just want to reiterate, this equation here is extremely important. This is our material relations equation. So this is analogous to the force deformation that we had before. It's called, this is called our torque twist relation, but it's similar in principle to your force displacement that we have in axial loading. This relates our deformation, which is now in terms of angles, to our applied loading, which is now in terms of torque. And so that's one of your pillars of mechanics and materials. That'll be the equation that you use when you're solving systems. The other two are going to be equilibrium, which now instead of being the sum of the forces will be the sum of your moments equaling 0. So the sum of the moments about the z-axis will have to equal 0. That's equilibrium. The second thing will be compatibility, but compatibility is going to be expressed in terms of angles once again. So when we do some problems next week, you'll see that we're looking at how these pieces need to rotate relative to each other in terms of, instead of how they're going to elongate relative to each other. And then the third piece will be this material relation equation. So, but to get from that torque to a stress, we need this torsion formula. So torque is the applied moment. Torsion is the stress that causes, the shear stress that's caused by the torque. And just a little review, we've talked about polar moment of inertia. J, we have two common cases. One is where we have a solid disk, and the other is where we have an annulus, so it'll be a hollow, like a pipe. J for a solid disk is equal to the integral 0 to 2 pi, 0 c, r squared d, r dr d theta, which if you integrate that, you're going to get pi over 2 c to the 4th. So that becomes the value for a solid cylinder. And if we are looking at an annulus, J is equal to the J of the outside minus the J of the inside. So that becomes pi over 2 C outside 4th minus C inside 4th. Any questions?
Before you go to the next slide, go back one slide. I want to see it.
Of course. All right, so we have plenty of time. Let's go ahead and do a little example. So we'll look at two cylinders in series. And we want to find the rotation. At point C. So I have, if I'm looking at this from the side, I have two different members. And we'll give those dimensions of L1 and L2. And we're going to apply a torque like this about the z-axis. So another comment in terms of our notation, this double arrow means moment, and you put your thumb in the direction that the arrow is pointing, and that tells you which way that moment is going. So this would be a positive torque. This first member is going to have properties G1, J1. The next member will be G2, J2. So presumably these are two different materials in addition to being two different cross sections. And we'll put points A, B, and C. And what we're trying to calculate is what is the rotation at that end, point C. So we always start with equilibrium. And now instead of the sum of the forces, it's the sum of the moments in the z direction are equal to 0. So whatever direction is that longitudinal axis is the direction that you're going to want to be taking the moments about. So before, remember in the past we broke this up when we were doing axial load and we had 3 separate things that we could take force diagrams about? Well, it's the same now. We have our free body diagrams. Okay, so we have our torque, which is going to have equal and opposite torque on the other end, which means this has to be equal and opposite. Then there's going to be some reaction here, and this continues all the way down. So remember we said that this first one and the second one were meaningless because they don't give us any new information. This is the torque applied. I shouldn't say they're meaningless, but this one on the right tells us that the torque 2 is equal to the torque. The one on the left tells us that torque 1 is equal to the reaction. So I guess those aren't completely meaningless statements, but they don't relate torque 1 to torque 2. Whereas here in the middle, what we see is a relationship between torque 1 and torque 2. So now, if we write out that relationship, torque 2 is positive because our thumb is pointing in the positive z direction. Torque 1 is negative because it's pointing in the negative direction. But I want to stop and clarify. There's 2 different sign conventions going on that can get you confused. One is the sign convention that tells you what effect it's going to have on the member. So remember on the positive side, I said if your thumb, well, on either side, if your thumb is pointing away, that's positive torque in terms of causing positive torsion in the member. Just like tension is always pointing away, that puts positive normal stress in the member. But equilibrium has an entirely different sign convention. So with equilibrium, it's whatever direction your thumb is pointing, positive or negative, that tells you whether that's a positive or negative torque. So they're both putting positive torsion into the member, but in terms of equilibrium, T2 is positive, T1 is negative, and they have to sum to 0, which tells us that T1 equals T2.
You said T2 is positive, right?
Yes, now. The way that I've done this math, they're both going to come out being a positive number because let me see if I can explain this. I'm assuming the direction, right? No, I'm not. They're both going to end up being positive numbers because the torque itself is positive, but it's pointing in, it's like getting attention. I always have to relate things back to axial loading because to me that makes a lot more sense. If you think back to axial loading, these would both be positive values, right? Because they're both tension. But when I make my equilibrium statement, I'd have a negative sign in there. But then, okay, so then T1 will equal T2. They'll both be positive values. All right, that's as far as we can go with equilibrium, right? We need to move on to mechanics of materials in order to see this problem through because we could have infinite solutions at this point. Actually, I take it back. If we know T, it's not infinite solutions. They're equal to each other, and because we know T2 is equal to T, they're all equal to that applied torque. If we're looking at kinematics, now we need to relate the rotations. So what statement can you make about the rotations of these members? What is one thing you know to be true? That is a true statement. Not the one I'm looking for. It's not something that we've talked about in the lecture so far. I just want you to look at that picture and tell me what you just put on your like practical mind. What has to be true when these two rotate? They're going to rotate in the same direction. And yes, where will they be the same amount of rotation? Thank you. Where they meet, exactly. So right here at point B, we have to have equal rotation immediately to the left and immediately to the right. So what we're saying is that the rotation at point B on the left is equal to the rotation of point B on the right. That is our kinematics statement. So kinematics is as simple as looking at this and really kinematics is common sense kind of. It's like look at the picture and explain how it moves, right? You look at it, you say, okay, I know that when things move, if they're connected, they're going to rotate together. You could have a scenario, if you want to make this a little more complicated, where you say one is allowed to slip relative to the other. So perhaps there's like a 20-degree slippage where you can apply torque and it'll rotate freely for 20 degrees and then it will engage. Now this becomes a little bit more of a complicated statement because you have to account for that 20 degrees rotation in there. But assuming that they're fixed together, as one rotates, the other will rotate at that plane as well. Okay, so we'll let that set and we'll go to our material relations. Material relations, this is something we talked about. This is our torque twist relationship. So Phi2 minus Phi1 equals TL over JG. So this equation is always talking about a change in angle. TL over JG tells you the amount of relative rotation. If one end starts at 0, then it's an absolute rotation. But generally speaking, this is a relative rotation equation. In this particular case, we're going to call A, well, we can do this for two segments. For member 1, we're going to get phi B minus phi A. We usually always go we usually always move in the positive z direction. So that means we're moving from A to B, which means we take the rotation at B minus the rotation at A. So final minus initial gives us the amount of change, which is T. We know that T1 is just equal to T, the applied torque, but it's going to be multiplied by L1 divided by J1 G1. And for element 2, now this is phi sub C minus phi sub B. That equals the torque, L2 over J2 G2. Now we know that the rotation at A is 0, correct? We have a fixed end. So that becomes 0. So therefore, this equation here is the rotation at B. And I guess if we're a little bit more specific, this one here would have been on the left-hand side, this one would have been on the right-hand side, but we know that those are equal. So we can take this equation. Here, we can take this equation and plug it in to our second equation. Right, the first equation gives us the rotation on the left-hand side of B. We know that's the same as the right-hand side, so we plug it into our second equation. And then we get that phi sub C, which is what we're actually looking for, right? We want to know the rotation of C. Is going to equal T times L2 over J2 G2 plus T times L1 over J1 G1. Yes?
The J and the G, those are like constants, right? Or like given.
Yes. Yeah, one's a material constant, the other is a geometric constant.
That should be G1 on the second part.
Yes, it should. Any questions? Okay. Well, that is torque. Next time, or torsion, next time we will continue with this topic.